In a previous video, we introduced hydrocarbons, and we talked about how that is a broad umbrella term that encompasses quite a few different types of molecules. So we discussed alkanes. We also introduced alkenes and alkynes. Alkenes are hydrocarbons that contain at least one carbon-carbon double bond. Alkynes are hydrocarbons that contain at least one carbon-carbon triple bond. So with alkanes, we said they were all single bonds. With an alkene, we have to have at least one carbon-carbon double bond. Notice that when that happens, each carbon already has two bonds, which means it needs two more bonds. So I'm going to give it two hydrogens. And the same thing on this side. And now if you hone in on each carbon, notice that each one contains four bonds, so it already has a completed octet. And it's good to go. So you'll notice that alkenes contains fewer hydrogens than alkanes do. And that trend continues on to alkynes, because an alkyne has a carbon-carbon triple bond. So each carbon really only needs one more bond to complete its octet. So the corresponding alkyne will have two hydrogens. Notice the geometry here. If you focus on this particular carbon here, you'll notice that it contains 1, 2, and 3 electron groups. It has no lone pairs of electrons, so this carbon has trigonal planar geometry. And that's the case for this carbon as well. So alkenes are going to be trigonal planar. Alkynes are completely linear, and they are always going to be linear. This is a 180-degree angle right here. So always draw alkynes as linear molecules. Both alkenes and alkynes are example of unsaturated hydrocarbons. Because they do not contain the maximum number of hydrogens that they could possibly have. So for example, if we were to compare these to alkanes, we say that alkanes are saturated because they contain the most hydrogens that you could possibly attach to a carbon. Notice if I attach 3 hydrogens to these carbons, they already have an octet, they have 4 bonds, there is nothing else that I could do here. Whereas with alkenes and alkynes, I could potentially break this double or triple bond and attach more hydrogens to those carbons. And we will eventually see that when we take a look at the reactivity of alkenes. So alkenes and alkynes are unsaturated, alkanes are saturated. Now that we've introduced them, we will take a look at naming these compounds. So let's start by naming alkenes. You will find that the rules are going to be very similar to naming alkanes, with a minor twist. We're going to change the ending, and we're going to have to prioritize that double bond when we are numbering the molecules. So the first thing we're going to do, as usual, is we will find the longest continuous carbon chain. But we have to make sure that that longest continuous carbon chain contains the carbon-carbon double bond or carbon-carbon triple bond if we are looking at an alkyne. So let's take a look at an example of how this could potentially go wrong. Okay, so let's say that I have that molecule. Typically, we start by numbering left to right, and usually what we do is we look for the absolute longest continuous carbon chain. And if I go in this direction, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. However, that chain does not contain the double bond, and I have to contain the double bond in my numbering system. So I'm going to start actually where the double bond is. I have 1, 2, 3, 4 carbons. And then I could either continue directly across. So that would give me 5, 6, 7, or an 8. Or I could potentially go up. That gives me 5, 6, 7, 8. In this case, it doesn't matter whether I go to the left or whether I go up, because in either case, I'm going to be generating a chain that contains 8 carbons. So keep in mind, with alkenes and alkynes, we want the longest chain that contains the carbon-carbon double bond or carbon-carbon triple bond, even at the expense of a longer chain. So we don't want the version on the left, even though it's longer, because it doesn't contain the alkene. The next thing we will do is number the chain to give the carbon-carbon double bond or carbon-carbon triple bond, depending on the molecule you're looking at, the lowest possible number. So when we looked at alkanes that had either alkyl or halogen substituents, we were prioritizing the substituents. Here we now have a higher ranking group. So you're going to give the double bond or the triple bond the lowest possible number, even if it comes at the expense of the substituents. So just be a little bit careful with that. That's an important rule change. If the parent chain is an alkene, we are going to end with -ene to indicate that it's an alkene. So we'll change the ending to reflect what type of functional group we have. And we need to indicate numerically where the carbon-carbon double bond starts. So let's do an example. And let's actually take that molecule that we looked at up top and go ahead and name it. Okay, so I'm going to start by numbering the chain, and I want to number it in such a way that the double bond gets the lowest possible number. So I'm going to start on the left, and then I'm going to continue up. Okay. So the fact that this chain has 8 carbons means I'm going to have the prefix oct to indicate 8 carbons. And then I'm going to give it an ending -ene because it's an alkene. But I do have to indicate numerically where that double bond starts. So you're always going to notice that the double bond is on carbons 1 and 2. You always want to give it the lower number. That's the start of that particular alkene. So we're going to call this 1-octene. And while we're at it, let's go ahead and name that substituent. So I see that there is a branch coming off of carbon 4, and it is 1, 2, 3, 4 carbons long, and they are connected all to each other in kind of a straight chain pattern. So this would be 4-butyl. Once you have that, it's really the same system that we've been using. We list the substituent first, and then the parent name. So the full name would be 4-butyl 1-octene. And that's the name of our molecule. Now, if the parent chain is an alkyne, then we will end with -ine, or YNE, to indicate that it's an alkyne. And same sort of thing that we saw with the alkene, we're going to indicate the number where the triple bond starts. And other than that, same sort of rules that we've been looking at. So I'll just copy this to the next page. I need a bit more space here. All right, let's try one. All right, be careful with how you draw alkynes in the line angle format. You want to make sure that that alkyne is linear. And I know it's very tempting, like if you've been drawing alkanes and alkenes, it's very tempting to do the zigzag pattern and then putting a triple bond. Don't do that. They are linear. They're definitely not bent like that. So just be careful with how you draw these. Okay, so the first thing I'm going to do is find the longest continuous carbon chain. And I see here it's pretty straightforward. If I just go directly across, I'm going to find the longest chain. I'm going to include that triple bond. Alternatively, you could have gone down instead of all the way to the right. It would end up generating the exact same chain length. Okay, so there are a couple of different ways I could number this. I could go left to right, or I could go right to left. Okay, and this is where we have to be careful, because thus far we have been prioritizing the substituent. So it's very tempting to use this version and say, okay, well, this gives the substituent the lowest possible number. But keep in mind, when we're numbering, we're actually prioritizing the carbon-carbon triple bond. So this is actually the version that we want, because this makes our triple bond start on carbon 3, whereas in the version on the right, it would start on carbon 4. And I want to give the triple bond the lowest possible number. So the version on the left is the correct one. The one on the right is not correct. Now that we have that, I'm going to list the parent name first. And I see that there are 7 carbons, so the prefix is hept. It's an alkyne, so it gets that ending -ine. And the triple bond starts on carbon 3, so I'm going to call it 3-heptyne. Now, notice that we have a substituent coming off of carbon 6. So it's attached to carbon 6. I'm going to list that. And it has 1 carbon. So that is a methyl group. And now that I have both the substituent and the parent name, I'm going to list the full name. So we would call this 6-methyl 3-heptyne. Let's try one more example. Okay. My bond angles are looking a little funky there. All right. So the first thing I'll do is find the longest continuous carbon chain. And it looks like directly across works. And I could have gone down either way. I'll end up generating the same name since it's the same chain length. And then I have to decide which way I'm going to number it. So I could either start on the left and go all the way to the right. One thing I would like to point out is that sometimes students get confused and they mess up the numbering here because they forget that there is a carbon on each side of that triple bond. So definitely don't forget to count those carbons. And alternatively, I could have started on the right-hand side and gone to the left. So now we have to decide which version we want. And notice that in either case, the triple bond starts on carbon 3. So here, the triple bond is not going to determine which path we take. And in either case, we have a substituent on carbon 2 and carbon 5. So we're kind of stuck in the sense that the triple bond and the substituent orientations did not choose a particular path. So we have to break the tie. And when there's nothing else at our disposal, we're going to use the alphabetical order of the substituents. Well, this is chloro. And this is methyl. And when we have to break that tie, we go by alphabetical order of the substituents. And while C comes before M in the alphabet, so I want to give chloro the lowest possible number, not methyl. So we're going to use the numbering system on the left-hand side. Now I'll go ahead and name the parent. I see that there are 6 carbons in the parent chain, so I'll use the prefix hex. I end with "-ine" to indicate that it's an alkyne. And then I want to indicate that the triple bond starts on carbon 3, so that's 3-hexyne. And then I'm going to list my substituents. So there is a chloro group on carbon 2, that's 2-chloro. And then there is a methyl group on carbon 5. And then I'll just list those in alphabetical order. So that becomes 2-chloro, 5-methyl, 3-hexyne. All right. The following rule applies only to alkenes. So don't mix this up with alkanes or with alkynes. This is a very, very common point of confusion. People do this with alkynes. It only applies to alkenes. We are going to use cis-trans terminology when carbons in the carbon-carbon double bond have different groups. Let's look at an example. Okay, so in this example, I'm going to color code these carbons. Or actually, let's number them. So I'll call this carbon 1 and this carbon 2. Notice that carbon 1 has 2 different groups on it. It has a bromo, and then it just has a hydrogen. And then carbon 2 has a hydrogen and a bromo. Well, these 2 groups are different from each other. So in this case, we're going to use cis-trans terminology to indicate whether these groups are on the same side of the molecule or on different sides. And here I see that bromo groups are on the same side of the molecule, so we call this a cis alkene. Now, alternatively, we could have put bromo groups on the opposite side of the molecule. So I'll number these again. So notice that carbon 1 has 2 different groups. It has bromo and hydrogen, and carbon 2 also has bromo and hydrogen. In this case, the bromo groups are on the opposite side of the molecule. Here bromo is facing up, here bromo is facing down. So definitely different sides of the molecule. If they are on the opposite side, then we call this a trans alkene. Notice this terminology only applies when the carbons in the double bond have 2 different groups. So I'll show you an example when we would not use that terminology. So what if I drew something like this? So here's my carbon 1, here's my carbon 2. Well, in this case, carbon 1 has the same groups. It has 2 bromines. And carbon 2 has 2 hydrogens. These are the same group. So in that case, we would not use cis-trans terminology because it doesn't really make sense. Like if I say cis, well, cis to what? These 2 hydrogens are the same, right? So we can't really tell if this is opposite of the hydrogen or if it's on the same side of the hydrogen. It's both. So the cis-trans terminology doesn't really make any sense here. So here we would not use it. You would just name it as a standard alkene using the same rules that we learned. And if you have a scenario where you are using cis and trans to describe the orientation of these groups, well, the cis-trans term is always at the very beginning of the name. So before you list anything else, even before the substituents. And of course, you're only going to use that term if it actually applies to that particular example. Okay, let's try an example. Okay, so I'm going to try a couple of different numbering systems, and then we'll decide which one is correct. So I could start by trying to go left to right, or I could try going right to left, and then we'll examine that further. Okay, so if I go left to right, notice that here the alkene starts on carbon 3, whereas if I go right to left, the alkene starts on carbon 4. And we said that we're going to prioritize the double bond. We want to give it the lowest possible number. So this version would be incorrect, and the one on the left would be the correct version. Let's name the parent. I see that it's 7 carbons long, so the prefix will be hept, and it's an alkene, so it gets the ending -ene. And notice that the double bond starts on carbon 3, so this would be 3-heptene. Then I'll list my substituents. Over here, I have a bromine on carbon 6, so that will be 6-bromo. And here we have methyl on carbon 5, so that's 5-methyl. And then I'll list the substituents in alphabetical order. And B is before M in the alphabet, so I'm going to list the bromo first. So this will become 6-bromo, 5-methyl, 3-heptene. But we have to be careful because notice, and I'm actually going to copy this to the next page so I can show you this in a bit more detail. Okay. Oh no, I deleted it. Okay, let's make this a little larger. All right, so I want to focus on that double bond. In the line angle model, we're not showing where the hydrogens are, but keep in mind that this carbon right now has 3 bonds, which means that there's a hydrogen here that we haven't been drawing in. So there's a hydrogen right here, and carbon 4 also has a hydrogen. Notice that these hydrogens are pointing in the opposite direction. Notice also that this bond is pointing up to the left, and this bond is pointing down to the right. So these groups are on the opposite sides of the molecule. They're pointing in the opposite directions, which means this is a trans alkene. And also, each carbon in the double bond has different groups. It has a hydrogen over here and then this ethyl group right here. The other carbon has a hydrogen and then this giant group right here. So this is a scenario where you would use this trans terminology, and it's a trans alkene, so we have to make sure we note that. And that will go at the very beginning of the molecule name. So this becomes trans 6-bromo, 5-methyl, 3-heptene. Let's try another one. Okay, right off the bat, you can probably tell that this is a cis alkene because it's kind of bent in that weird way. And if you focus on the carbons in that double bond, notice that each of them only has 3 bonds right now, which means there's a hydrogen right here and there's a hydrogen right here. And these groups are both pointing down, so they are facing in the same direction. So this is definitely a cis alkene. Now I'll look for my longest continuous carbon chain. It looks fairly straightforward. If I could just go directly across, I'm including all of the carbons. And then I have to decide which way I'm going to number this. So I'll try a couple of different versions, and then we'll take a look. I could count left to right, in which case my double bond starts on carbon 4. Alternatively, I could count right to left. And in that scenario, the double bond also starts on carbon 4. So in this case, the double bond doesn't really care which way we go because in either case it has the lowest possible number. So the next thing I'll do to break the tie is to look at the substituent. And I see that in the bottom version, the substituent is on carbon 2, whereas in the top version, the substituent is on carbon 7. So since the double bond is already taken care of, I'm going to choose the version that gives the substituent the lowest possible number. So I would use the bottom numbering system, not the top one. Then we'll identify the parent name. There are 8 carbons in the longest continuous chain. So the prefix is oct. It's an alkene, so it gets the ending -ene. And the double bond starts on carbon 4, so it's 4-octene. Then I see that the substituent is a fluoro on carbon 2, so I'll call that 2-fluoro. And then I'll put all of that together. Note that the cis terminology is listed first, then the substituent, and finally the parent name. And that becomes cis 2-fluoro 4-octene.